Alright, hello, and welcome to part 2 of Math3411. Hopefully you've been enjoying the course, and thank you so much to Jess who did the first part. Now we'll be going on to chapter 4, and chapter 4 is going to be about information theory. Theory about information. Except, of course, maybe we need a bit more than this. We might need to know what information exactly might be. And in our case, we define information as maybe like a number, and the number represents how surprised you might be to see a given scenario. So let's give an example. Let's say that we have source S1 and S2, which means you can either get an S1 or an S2. And we can get S1 99% of the time, and we get S2 1% of the time. So if we get S1, we're like, hey, we're getting this like 99% of the time, right? We don't really like care too much. It doesn't really surprise us. So compared to getting an S2, which is a lot less likely, we'd be a lot more surprised, right? So we'd say that S2 gives us more information than S1. But how exactly do we reach this number? Well, we have a formula. It's pretty handy. Essentially, if we have a code in radix R and an event of probability P, then we can say that the amount of information that we have is given by minus log RP. So if we use our previous example, let's say that we had radix 6. Then the amount of information that we get from something like probability of 1%, it would be given by I of 0.01, which is minus log base 6, because we have radix 6, of the probability. If we put that into our calculators, we get 2.57 ... And if we put in 99%, then we get 0.0056, which is a lot less since we get a lot less information. Right, so hopefully that makes sense so far. And we have property to have a few properties. Sorry about this, I'm a bit sick. So the first thing is we need information to be at least 0. Obviously, information, you either have information or you don't. You don't have a negative amount of information. The next one is if two events happen, let's say we get S1, S2, and these two are independent, then their probability would be 0.99 times 0.01. But we also want the information that we get from getting these two symbols to be the same as getting the first symbol, S1, and then getting the information of the second symbol, S2. So what that means is when we have two events which are independent, we can essentially split up their parts to get the information of each individual part, and that's the same as the amount of information we get as a whole. And then, of course, we need the information to be a continuous function. All right, let's get to entropy. So what is entropy? Well, let's say that we have a source S and it has a bunch of probabilities, P1 all the way to PQ. And we also know that it's radix R. Entropy, you can think of it like the expected value for information. So you might remember the expected value formula is the sum of all probabilities multiplied by their weights, right? So we had xi, and I ranged from something like 1 to Q. And we're doing the same thing, except in this case, it's the probability and the value that we're expecting is information. So we replace this xi with information and we get I. It's base R, so we have R here, and then the probability. If we use the formula from before, we can just substitute it back in and we get this. So our entropy, which is the expected amount of information per symbol, is minus sum of pi log base R of pi. Right, this is the probability, this is the information, and then we just sum it up for all available probabilities. And usually we work in base 2 in our case, we use the radix 2. So if R is equal to 2, then you might see a H without any subscripts or number below, and that means that we have radix 2. So, how might we use entropy? Well, the first thing that this question wants us to do is calculate the average length with a binary Huffman code. Although, thank you to Jess, we already know how to do that, so I've just skipped that part. We have an average length of 1.6. And how do we calculate the entropy? Well, it's going to be the sum of all probabilities, where for each probability we do minus 0.6 log, and since this is binary, we have base 2, then we have 0.6, and that's our information for the first probability. We add that to the second probability, this information, the third probability's information, and the, whoops, my fault. And the fourth probability's information. And if we sum this all up, we get 1.5709. And this is the way you could interpret entropy. You can think of it as the number of bits of information that are needed to be able to represent this specific source symbol on average. So it says on average, we need about 1.57 bits of information to represent each source symbol. So that's why the average length is 1.6, because 1.6 is greater than 1.57, so Huffman code has at least 1.57 bits on average to be able to represent each symbol. And we also have a maximum entropy theorem, and it basically just says, for any entropy that we have, it always has an upper limit of log base R Q, where Q is the number of symbols. And this is something that you should know the proof of, and this is in the notes, so I won't go through it, but you do need something called Gibbs inequality for it. And what Gibbs inequality says is, if we have P1 to Pn, which is a probability distribution, that means that they're all probabilities and the probabilities sum up to 1. And we had a second distribution, which means they're also all probabilities, so between 0 and 1, and they sum up to 1 as well. If we calculate the entropy, this is always less than or equal to the entropy, except inside the logs, we replaced all values of Pi with Qi. And the way you can think of this is like, we're making a bunch of changes to Pi. We're jumbling the P probabilities up, or maybe we're changing the values, right? So one possible change could be adding some value to P1 and then taking that value away from P2 to create the Q values, or maybe you might be doing a swap where Q3 is equal to P1, P4, and Q4 is equal to P3. So we're just saying for any other probability distribution, if we calculate the entropy with that, then it's always going to be greater than or equal to our original entropy. This one fact is mainly used for proofs, and you should also probably know the proof of this, since this is what Thomas had said in his examinable concept. Now, we get onto first source coding theorem, and this is something that you should know the proof of as well. It says if we have a source S1 to SQ with the related probabilities of P1 to PQ, then we can say that C is a uniquely decodable radix R code word with lengths of L1 to LQ, and we have an average of LR. Then we say that the entropy is always less than or equal to the average length. And that pretty much entails what we saw in the first example, right? We saw, hey, the average length of Hoffman is actually greater than the entropy. And the reason of that is because the entropy represents how many bits of information you need on average to represent these source symbols like S1, S2, all the way to SQ. And L is our average length for the code word. So, since you always need the entropy amount of bits of information on average, our average length is always going to be larger than our entropy. We also get equality if the probabilities are equal to R to the power of minus Li, and our Kraft-Macmillan constant is equal to 1. You might be wondering, hey, we know about information, but how do we actually use information? Well, we just said, hey, we know that the amount of information for S1, for example, so this represents the number of bits that we need to represent S1, so we can actually use this as a basis. For the ith source code, we know that this is our information, and by taking the seal, we can take a value which could be like 0.8 and then turn it into a whole number, since obviously we only have a whole number of symbols. And since the information says, hey, we need at least 0.8 bits to store this SI, then we can use 1 bit to store this SI. And so what Shannon-Fano has us do is, for each probability, we calculate L1, L2, all the way to LQ. Then, using these lengths, we can actually just find out the standard I code with the decision tree. To see this in action, we might look at this example. So, we have S1 all the way to S5, and we have the probabilities 0.4, 0.2, 0.2, 0.1, 0.1, and we know that it's in radix 3 because it's ternary. We want to use Shannon-Fano code for this source, and so the first step we do is we try to find the lengths of each code word. And we know for S1, since it has a probability of 0.4, our length is going to be the ceiling of the amount of information we get. And if we calculate that, we get minus log base 3. 0.4 is going to be equal to 0.83, and so on. And if we seal that, we get a 1. So that's how we know the length of 1. And we can find the length of 2 and 3 by taking the seal of minus log 3, 0.2, and so on. And the other useful thing is that if we have two probabilities which are the same, then we also know that they have the same length, since the amount of information we get is the same from each source code. So this is how we get the lengths. We have 1 for L1, 2 for L2 and L3, and then 3 for L4 and L5. Now, we can use our standard I-code decision tree to find out the actual code words. We can start off with a 0, and we've reached our source code length of 1, so that's S1. Now let's try 1, and in here, we know that we want 2 code words of length 2, so by fulfilling these 2 lengths, we get S2 and S3. Then we can use 2 right here to create 2 more code words of length 3, and that gets us S4 and S5. And what we notice is, for S1, our code word is just 1, S2, our code word is 1, 0, S3, 1, 1, S4, 1, 2, 0, and so on. So it's pretty standard once you get the lengths. And these are our code words. And I missed a bit up here. Essentially, you might be wondering, hey, why are we using Shannon-Fano instead of Huffman? And the thing with Huffman is, it is actually better or equal compression to Shannon-Fano, so if you have all the probabilities, it's always better to go with Huffman to get a better code. But the thing with Shannon-Fano is, we only need P1 to find what the length of the first code word is, right? It's independent of the other probabilities, so Shannon-Fano means you can actually find out length without having to actually get all the probabilities, right? Because Huffman, it requires you to have all the probabilities. You need to be shifting all of the probabilities around as you combine them into new probabilities and so on. And so that's why Shannon-Fano might be more reasonable for you. If you have probabilities you don't know, then it might be better to try out Shannon-Fano. If you do know all the probabilities, then try out Huffman. And Shannon-Fano, while we said that it wasn't as good as Huffman, it's actually not a bad code. And the reason that is because we actually know that Shannon-Fano's compression is always less than or equal to the entropy plus 1 on average. How do we prove this? Well, I've given a sketch because it's something that you do need to know the proof of. Let's start with the left-hand side. We could either use the fact that the entropy is always less than or equal to the the average length, which is from our, up here, the first source coding theorem. Or we can do it specifically for Shannon-Fano in this way. We know that the entropy is always equal to minus the sum of pi times log base r pi. And we know that if we take the ceiling, then we can say that it's greater than or equal to the ceiling, right? So if we take the ceil of any value, then we're essentially always increasing the value. So we know that this is less than or equal to this value. And of course, this is just our average length, right? Because this is our Li, and we're having a weighted sum of the lengths in SF. Now let's try to prove the other side. Well, we know that the average length is going to be equal to the expected length of our length right here, which is given by the formula where it's going to be the sum of pi multiplied by the length at I. Then we know that this is actually less than or equal to this sum, And the reason is because anything which has been sealed is less than x plus 1, right? If it's a whole number, right, like 2, then the seal of 2 is just 2, and 2 is equal to 2 plus 1, sorry, less than 2 plus 1. But if it's a number in the middle, maybe something like 2.5, if we seal it, then it just rounds up to the next number, which is going to be 3, but that's rounding up is always less than 1, so we say that this is less than 2.5 plus 1. So we know that when we seal something, it's always less than the seal of minus log pi is less than minus log pi plus 1. And so what we can do is we can split up this sum, right? We can distribute the pi to the log and also the 1, and that gives us 2 sum terms. We know that P1 to PQ, that's a probability distribution, so the sum is equal to 1, and this is just our entropy. So now that we know that Shannon-Fano is bounded, whilst it isn't as good as Huffman, it is still a relatively good code. So how might we actually find the entropy of extensions? So you might remember extensions from before. We have something like S of 3, and that represents maybe the set of all symbols which have, the set of all code words with length 3, given with these source codes. And the problem with this is, when we're trying to calculate the entropy, we have to find the probability of each individual permutation, but there are a lot of permutations, right? Even at S3, if we have 2 symbols, then we have 8 options. When we have S4, we have 16 options, and so on. So it increases rapidly, and our sum becomes larger and larger, right? Because our entropy sums up all the probabilities. So to simplify this, we have a formula where it just says if we have the nth extension, then the entropy is the same as n times the entropy of the original code. Now we can use this fact where we know from our previous slide that the length of Shannon-Fano is going to be greater than the entropy, but less than or equal to the entropy plus 1. We can now use this rule from above and bring the n down. Now if we divide all sides by n, we see that as n gets larger and larger, this term becomes a 0. And so if we take the limit of this middle term as n goes to infinity, then we actually see that since this becomes a 0, we actually just get the entropy on both sides. And so this limit right here must be equal to the entropy. So you might get a question that just says, hey, calculate the average length per original source code as n goes to infinity, and to do that, you just calculate the entropy. Now, the entropy is calculated for sources, and what's another source that we know? Well, we know Markov sources, right? So we also go through how do we calculate the information and entropy for a Markov source. Well, we know that a Markov source might be given as a matrix, an n by n matrix, in this case S1, S2, and S3. S1, S2, S3. And let's say we wanted to get the information from receiving Si, given we know that the previous symbol received was Fj. So if we wanted S1, given we know that we just received an S2, we would look at this column since we just received an S2, and then this one right here is our probability. So turns out we can just use this probability and apply our information formula. So we can do minus log and then p of 1, 2, which says the probability at the row of 1 and column of 2, which gives us this probability right here. Now that we know how to find the information, then we can use information to calculate the entropy. And the entropy is just the entropy of the source S, given that we know the last symbol is Sj. And turns out it's actually just the entropy for a given column. So H of S given S3 is our last source symbol. We can actually just find the entropy of our final column, because that's the probabilities we have given that we just received an S3. And so that's pretty much what our entropy is. It's just the entropy of the jth column to get HS given that we just received Sj. And now we can use that to get our Markov entropy, which is the entropy in total, and that's given by the sum of Pj multiplied by the entropy given that we just received Pj. Right, so we also have the equilibrium entropy, and that's just the entropy of the vector that we usually get. So we might see up here, we have an equilibrium vector. We just take those probabilities and calculate the entropy based on that. So let's actually quickly calculate the entropy of this Markov source. The Markov source isn't actually correct in this case, but we just use this example as a way to show you how we might be able to calculate the Markov entropy and the equilibrium, given that we just received S1, H of S given that we received S2, and H of S given that we received S3. And the reason that is because when we're calculating the Markov entropy, we need to find these values and then multiply it by our Pj value. So the way we can do that is we know that this is just the entropy of the first column, this is the entropy of the second column, and this is the entropy of the third column. So when we calculate these, we might see it's just the sum of 0.3 times the information given by a probability of 0.3, right here, 0.6 times the information we get from a probability of 0.6, and so on, and that's how we find the entropy, given that we just received an S1. We can do the same with the probabilities from the fact that we just received an S2 and S3, and that's how we get our conditional entropies. And now we know that the Markov entropy is given by the probability we get an S1 multiplied by the entropy, given that we just got an S1. We also have the probability that we get an S2 multiplied by the entropy, given that we just got an S2, and then the probability of S3, given that we just, the entropy of when we just got an S3. And by calculating that, we get 1.30. And then we have our equilibrium entropy, and that's just equal to the entropy of this p vector, which would just be minus 0.53 log base 2, 0.53, minus 0.15 log 2, 0.15, and so on, right? Just calculate the entropy as you would normally. And something we know is that for a Markov source, the Markov entropy is always less than or equal to the equilibrium entropy. And the way you can think of this is maybe from this example, right? When we calculate our equilibrium entropy, we only use these probabilities, but when we calculate a Markov entropy, we actually get a lot more information, right? Let's say that we just got an S1. Well, if we get an S2, then we're not too surprised, right? Because we know after getting an S1, it's very likely that we get an S2. But let's say we just use the equilibrium. If we got an S1, we don't really care about what we just got. We just care about the thing that we currently got. And in this case, we see that it has a chance of 0.15, which is the lowest probability, and we'd be a lot more surprised if we see that if we use the equilibrium. So the reason our Markov entropy is less than our equilibrium entropy is since we know a lot more from our Markov matrix, we are a lot less surprised when something that seems unlikely with just the equilibrium happens. We also have extensions for the Markov source, right? We have the Markov source entropies, which use these formulas, although I really wouldn't pay attention to them because I feel these ones might be a bit more appropriate. We have the same thing for the Markov entropy. We can bring the n down like we did before, and so the Markov entropy of S extension n is just n times the Markov entropy. And for the equilibrium entropy, we see that the nth extension is actually just E, the equilibrium entropy by itself, plus n minus 1 times the Markov entropy. And we also know that the entropy of the equilibrium to the nth extension over n has a limit of the Markov entropy, and that just is similar to the limit we have above here, which is that the average length per source symbol becomes the entropy. So, now that we've finished everything with Markov sources, let's move on to noisy channels. And what is a noisy channel? Essentially, noisy channel is when we have a source, which is A right here, essentially the set of all symbols that we can send over, and then we have a sink or the output. And that's the set of symbols that we can get back. Usually, if we send an A1 and that corresponds to a B1, then that's all we get, right? If we send an A1, then we'll get a B1 back. But the thing with noise is it jumbles everything up. So you're never guaranteed to get a B1. So if you send an A1, there's a probability you can also get back a B2. And these source symbols, A1 to AU, have their respective probabilities, and so do these sink symbols. So, what we might want to know is, how do we actually calculate the entropy of a noisy channel? Well, we first have HA, which is the source entropy. It's the entropy of all the symbols we're putting into the channel, and that's just the entropy using these probabilities. Similarly, we have HB, which is our output entropy, and that's just the entropy of the symbols that we receive, and that's given by the entropy calculated with these probabilities. Now we have conditional entropies. What's the entropy of the output, given that we know that the sent symbol is AJ? And we see that this is actually just the normal entropy formula, except we've replaced our probabilities with probabilities given that we've just received an. So this is just the probabilities that you might see in an entropy formula, except it's replaced with the probabilities AJ, given that we know that the output is PI. And we can use this to find the noise entropy. And you can think of it like the entropy of the output given that we know what the input is. And that's just the probability of sending out an AJ multiplied by the entropy that we of our output, given that we know that we just sent an AJ. And we also have the channel equivocation, which is the opposite. What's the entropy of the input, given that we know what the output is? So it's the probability of our output, BI, and the entropy of the input, given that we already know what the output is, which is BI. Then we also have the joint entropy, which is HAB, although I don't really pay attention too much to this formula because we'll give you a better one shortly. So the first thing we want to know is, what is the entropy of B given A? I've already told you that. It's just the average information of the output given we know the input, and A given B is the same thing. It's just the average information of the input given we know what the output is. So what's the joint entropy? Well, you can think of it like the average information overall in the channel. And it looks at every single pair of input and output that we could possibly have. And now we have the formula for joint entropy, and it just says the joint entropy is just the information we get from the input and the information from the output given we know the input. Or vice versa, it's the information of the output and the information of the input given we know what the output is, right? Hopefully that's pretty intuitive to why that's the information of the channel overall. I might take a bit of a break with some water. So, we know that from our previous formula, these two terms are equal to each other. And what we might do is, we know that it's also equal if we minus a HA on both sides and HB on both sides, and we get this right here, which is HA minus the entropy of A given B, which is equal to HB minus the entropy of B given A. And we call this the mutual information. And what it calculates is the value of how much seeing the input would reduce the uncertainty in seeing the in B, and vice versa, right? So you can see that this formula might be the entropy of the output minus the entropy of the output given that we know what the input is. So what's the level of surprise you'll get if we already, essentially it's just this. It measures how much seeing A reduces how uncertain B would be. And these values are actually pretty good because we can use them to calculate each other. And this is a thing that you might have seen in Thomas Britz's notes. Essentially, it just says how big each thing is, right? We know that the joint entropy is HA plus HB given A. We also know that the joint entropy is HA given B plus HB. We know that these two are equal. we know something like this HA minus this HAB gives us the mutual information, and so on. So this just lets you come up with a bunch of different formulas to calculate each value if we know the other values. So we might know a previous formula from our test in week 10, and that was the joint entropy is going to be equal to H of A plus H of B minus the mutual information. And so you can use this table to come up with different formulas and different ways to come up with each value in here. So let's go through a bit of an example. And the first thing we need to know is, this is actually very useful, where in binary channels, which means we can send out or receive two symbols. Let's say A is going to be equal to S1, S2. We say that A is a binary channel because there's two things. And what we might notice is that the actual entropy of A is going to be probability of getting 1 multiplied by the information of getting that 1. But then it's going to be the probability of getting the other source. Obviously, if the probability to get the first thing is P1, then the probability to get the other thing is going to be 1 minus P1. And we can use the same probability in our information formula. And we get this formula. And so it turns out, to calculate the entropy of a given binary channel, we only need one probability, right? Since one determines the other. And so we have a bit of a formula. It turns out H of A is going to be H of P1, which is also H of P2, where P2 is 1 minus P1. And that's why this formula is very useful. We can use this formula in binary channels to calculate the entropies. So in this question, we want to find HA and HB given A. We know that A is binary, B is binary, and so we can actually use this fact since we know what the probability of PA is. And we realize, hey, HA is actually just equal to H of this probability, which is X. And if we expand it out, this is what our entropy turns out to be. And we can also get the conditional entropy. And this is the entropy of the output given we know the input. So there's two possibilities, right? Our input could either be A1 or the input could be A2. And for each, we would calculate the entropy of the output given we know what the input is, which is B1 and B2 respectively. And the reason why this is so useful is because the first thing is we know what PA1 and PA2 are, right? PA1 is X, so PA2 is 1 minus X. But the second thing we know is these two values. And the entropy of the output given A1, since that's a binary channel, we actually realize, hey, this is equal to the entropy where the probability is B1, given that we know that we're getting A1, which is just 4.4 over 5. And so we only need to find the entropy of 4 over 5, and we can use the formula above to calculate that. Similarly, we know that H of B given A2 is just the entropy of the probability of getting a symbol in B, knowing that we already received an outgoing symbol of A2, and this is just 4 and 5 as well, so we see that this is H4 and 5. So what we realize is, when we substitute in our probabilities, since these entropies are the same, H of 4 and 5, this x term and this minus x term cancel, and overall we just get H of 4 and 5. We can use the formula from above to calculate it, and we get 0.722 to 3 decimal places. Now, we want to calculate the entropy of B and the mutual information. So, how might we calculate the entropy of B? Well, the first thing we might want to do is, since we know that H of B is just the H of any symbol in B, we might use that fact to find out what the probability of B is. And the probability of B1 would just be the probability that we sent out an A1 multiplied by the probability we receive an E1 given we just sent out an A1, right? Plus the probability we sent out an A2 multiplied by B1 given we sent out an A2. And the reason is because there's two ways we can get B1, right? We could send out an A1 and then receive a B1. Then we could send out an A2 and 1. Oops. And what's the probability we send out an A2? What's the probability we get back a B1? Well, we know the first probability right here, which is 4 on 5. And we know that PB2, given we just received a A2, is equal to 4 and 5. Well, we know that there are only two symbols, B1 or B2, so the other time we must receive a B1. So the probability we get a B1, given we sent out an A2, is 1 on 5. And using this, we can calculate our probability, which is going to be 1 on 5 plus 3 on 5 times x. And using this, we can actually find H of B, which is just H of our probability. Now, let's use it to find our mutual information. What is our mutual information? Well, we know that it's just HB minus HB given A, and so we can substitute our values in, right? We found HB here, and we found H of B minus B given A here, and so we can join those values and then plug them into the formula, and we get this. You can expand it out if we want to, but I believe this should be sufficient. Now, let's learn about channel capacity. And channel capacity is just the maximum information that you could get given all possible probabilities of A. So, your goal is just to find what's the probabilities in A, which would give you the maximum information, and then using those probabilities to actually calculate that information. So, how might we find the channel capacity of our given example? Well, the first thing we might do is we might take our entropy formula and differentiate it. And the reason is because we're trying to find the maximum of something, and the way you do that is you could take the derivative, find where it's equal to 0, and that's your max point. And so when we take the derivative, we see that we get log base 2 of 1 on x minus 1. So we also have the mutual information from our previous question, and we see that there's only one unknown variable, which is x. So our goal is to see what x value gives us the maximum information. So if we take the derivative of information, we know that this is constant, so this just becomes a 0 in the diff, and we take out this coefficient from chain rule, then we substitute this value into our formula above, right? So this x is replaced by our value right here. And now our goal is just to solve for when this is equal to 0. Once you do that, we get that x is equal to a half. And so now that we have that, to calculate the channel capacity, we'll just substitute that half in and then find the value. And in this case, it's going to be 0.278. And that's pretty much it for the first part, which is chapter 4. And now let's move on to chapter 5, which is going to be number theory and algebra. This chapter uses quite a bit of division and moduluses, so be prepared. But we just need to know some basic facts first. We know that for any two numbers, a and b, in this case where a is greater than b, we can represent a as a multiple of b plus some remainder. And this comes from division, right? Where a on b is equal to some quotient plus a remainder. And in this case, we just multiplied all sides by b. Well, we call q the quotient, as I said, and r the remainder. And we would say, in mod terms, a is equal to r mod b. And in mod b, it just says, if we divide both numbers by b, are the remainders the same? If the remainders are the same, then both numbers are the same. Now, if the remainder is 0, then we say that a is a multiple of b is a factor of a, or that b divides a. And so you might have seen a vertical bar. That vertical bar just means b divides a. So you can read that vertical bar as a divides, right? So let's go into calculating the greatest common divisor. And the greatest common divisor is just the biggest number, which is a factor of a and b. How might you go about that? Well, we have a formula. Well, an algorithm. The algorithm just says, let's take our values a and b, divide a by b, and that gives us a remainder, r. Then what we can do is replace this a with a b, and then the b with an r. And so what we're going to be doing is we continue this until this remainder is equal to 0. And once we've done it enough, we know that this previous non-zero remainder is going to be our greatest common divisor, and so that's what we return. We also want to look through a bunch of inverses, so we're just going to be building up and giving you a bunch of knowledge, which lets you tackle the questions in this section. And the first thing we might need to know is what an inverse is. Essentially, we have an element in Z of m. Z of m is just the set of integers 0, 1, all the way to m minus 1. So they're the numbers such that it's in the world of mod. And let's say we take a number from there. We say that a to the power of minus 1 is an inverse, right? This is an inverse if, when we multiply by that number, we get 1. If we multiply that number by a, we also get 1 in mod m. And that's what we call an inverse. But inverses don't always exist. So when do they exist? Well, they exist when a and m have a greatest common divisor of 1, which you can find from the Euclidean algorithm. So if GCD is 1, then it has an inverse. Now, we look at units. Well, what is a unit? A unit is just the set of all invertible elements, right? And since we know that invertibility and GCD equals 1 are equivalent, we can also say that this is just the set of all elements in Zm such that the GCD is equal to 1. So, this is also in modern, by the way. And we call these elements units. There's something else. We know that if m is prime, then the units are just all the numbers from 0 to m minus 1. And the reason that is because if a number is prime, then it doesn't share common divisors with any other number, which is unless the actual prime is a factor, right? So what that means is, since Zm is the set of all numbers 0, 1, all the way to m minus 1, and these numbers are all less than m, if m is prime, then all of these have a greatest common divisor of 1. We also have Euler's phi function, which is pretty useful, which we'll see later, and it's essentially just how many units does Zm have, right? What is the size of um, and what is the number of units such that, number of elements in Zm such that the GCD is equal to 1. It might be a bit hard to calculate, but we have a couple facts to help us. The first one being, if the GCD, if m is equal to AB and AB have GCD 1, then we can split it up. So an exam question you might have seen is finding phi of 77. Obviously 77 becomes 7 and 11. Both of these are prime, so they have a GCD of 1, we can split them up. And if p is prime, like 7, we know that the phi is just p minus 1, so it's 7 minus 1, or 6. And similar here, it's just 11 minus 1, which is 10. So in total, we get phi of 77 is 60. We might also get the fact that we get a squared, right? So 7 squared, we have a formula for that. It's just 7 squared minus 7, 2 minus 1, so that's 7, and that's just 42. So if we have p to the a, where p is prime, then we get that phi is just p to the a minus p to the a minus 1. And then the final thing, if we have 3 to the 6 and 5 to the 7, since 3 and 5 are not the same, these two numbers are also co-prime and don't share any factors with each other, so the GCD is equal to 1. And what that means is, if we have phi of this number, we can actually just split it up to phi of 3 to the 6 and phi of 5 to the 7. So we also have Fermat's little theorem, and it says, if p is prime, then a to the p minus 1 is equal to 1 in mod p. But this is actually just a special case of Euler's theorem. And Euler's theorem says, if we have a and n, and their GCD is 1, then a to phi n is just equal to 1 in mod n. And what we realize is, if n is prime, then phi of n is just n minus 1, which is what we see here. And that's pretty much it, right? It's just an application of Euler's theorem. Now let's get on to primitive elements. We define order as the minimum power for a such that a to the power of k is equal to 1, mod m. And keep in mind that a has to be a unit. Why is this important? Well, we can use this to define something called a primitive element. If the order of an element G is the same as phi m, then we say that it's primitive. And the reason it's primitive is because we can use it to calculate the rest of the units. Because it turns out in mod m, all the powers of g from 1 to phi m, they all become the units. And that's why it says g, because g actually stands for generator, so you can use it to generate the units. We have some facts about primitive elements. The first one being, if a is a unit, then the order is a factor of phi m, which means that when we're trying to find out what the order might be, rather than having to try out every single number in the k spot, we can actually just try out k, which is a factor of phi m, which drastically reduces the number of choices that we have. The next one is primitive powers. Essentially, if g is a primitive element, then g to the k is primitive when k and phi m have a GCD of 1. Phi of phi m are the number of primitive elements. Why might that be? Well, we know that phi of m is the number of elements such that the GCD of a number and m are equal to 1. In this case, we want to know the number of elements such that the GCD of k and phi of m are 1. So, turns out that's just phi of m. Because to get phi of m, we're just replacing that m with the phi of m. Now let's set up what a field is. A field is essentially just a set of numbers that can add, subtract, divide, and multiply. So you might think of the real numbers, for example, right? We can add, subtract, and multiply them. And the thing with these is we do need some rules because otherwise some wacky stuff could happen, right? So the first thing is, if we take two numbers in the field and we add them, then that must still be in the field, right? Like, if we added two numbers and then it was outside the field, then we would no longer be able to use that number, right? So that's why we have closure. We have the same thing with multiplication, where if we know that x and y are in the field, then x times y is also in the field. We also know that we have associativity. It just means it doesn't matter what order you add and multiply things, right? Adding the first two elements first, or adding the last two elements first, or same with multiplication, this is all the same. And the next thing is commutability. It just means it doesn't matter what order the elements are in, right? X plus y and y plus x are the same, and similarly, x times y and, right, it's still going to be a 1. We have an identity element for multiplication 2. If we take 6 and we keep multiplying it by 1, it's still going to end up as a 6. And we need negative elements. That just says if we have a number x, then we need a number minus x, such that if we add them together, then we get 0, which is our identity. We have the same thing with multiplication. If we have a number x, then we need some number x to the minus 1, such that when we multiply them, we get a 1. So if we have 1 and 5, then 5 on 1 is going to be its inverse. Now we have distribution, which just says we can take this x and then distribute it to an addition. We can take this x and distribute it to an addition. And that's pretty much all the rules. There are, I think, 12 of them in total, but overall, we need them because each one makes sure math doesn't break. And we also know a rule, which is essentially, if z of p is a field, then p is a prime and vice versa. So z of p can only be a field if p is a prime. And the main thing that might be why this is because some elements in Z of M, where M is not prime, don't have inverses, right? So if it doesn't have an inverse, then we've just failed one of our rules. So by definition, it can't be a field. We also have polynomials. You know what a polynomial is. The main difference is just that the coefficients have to be, whoa, that's not, whoa, part of the field. And we have some other definitions for polynomials, such that if the first thing is a 1, then the whole polynomial we call monic. If the first coefficient is non-zero, then we can say that n is our degree, and we have this notation, which is f of z square bracket x square bracket, and that means the set of all polynomials over f. So you might see this later. If we have z of 2x, that just means all the polynomials with coefficients from z2. We also have division in these polynomials, which we can do by polynomial division. And it just says, if we have two functions, f and g, then we can represent f as q times g plus some remainder r, as long as q and r are polynomials, and they are also unique for f and g. So what that means is the remainder is always the same if we already know what f and g are, and the quotient is always the same. We also have remainder theorem, which is essentially where we have g is equal to a linear factor. And what we find is, in this case, the remainder is always going to be the value at c. And we can use this for factor theorem, and that just says if this remainder is 0, then we know that this linear factor is actually a factor of f. And we also call c a root of f. Let's just define some other things. We say that f is irreducible if it has no proper factors. We chuck in all the numbers from f. If none of them are factors, then f is irreducible. We also have the polynomial modulo. Essentially, if we have the set of all functions in z with coefficients in zp and a function f, then zp bracket x bracket over angle bracket of f, we know that this just says the function in zp mod f. And now we can build up to our final big theorem, which is finite field theorem. And it basically just says, if we have p is prime, m is monic and irreducible with a degree of n, and a is a root of m, then we know that the set of polynomials in zp modulo m is a field. We also know a couple other things, such as f being a vector space of dimension n, f having p to the n elements. We know that 1 alpha squared all the way to alpha n minus 1, that's a basis. And if we get a primitive element g of order pn minus 1, then our field can be represented by 0 and then the powers of g from 0 all the way to pn minus 2. So there's a lot of facts here. Usually you might just see the main one, which is that it is a field, And maybe you might get some questions on the actual dimension or the amount of elements that you might have. So let's look at an actual question. In the question, they give us the polynomial, which is x squared plus x plus 1. And we know that we're working in the field Z2. So in Z2, the numbers are just 0 and 1. Let's say alpha is a root of m1. Usually we have to do the multiplications ourselves, but they're pretty simple. The first thing we need to know is alpha is a root of m1, so subbing it in as 0, which means alpha to the 4 plus alpha plus 1 is equal to 0, which means alpha 4 is equal to minus alpha minus 1. But since we're in modulo 2, we actually notice that minus 1 is equal to 1 mod 2. So this is actually just alpha plus 1. And to calculate a to the 5, then we just multiply all sides by alpha, and then just use this substitution when necessary. So since we have the table already, it should be pretty simple. We have a fraction right here, and our goal is just to simplify it into a power of a. And the way we do that is, I would like to call this our basis or base elements. And what I do is, I just want to transform everything into those elements. If we see a power greater than 3, then we can look at the table. A to the 11 is this right here. So we substitute it right here. A to the 8 is right here. So we have the alpha squared plus 1 here. We know that since 1 plus 1 is equal to 0 in mod 2, these cancel and these 1s cancel. And now we get 2 more expressions. We can actually use the table again, where we know that the top is just alpha to the 5, the bottom is just alpha to the 9, and we get alpha to the minus 4. And what we realize is, if we do this calculation again, right, we have alpha to the 14, which is a to the 4 plus a. We can use this substitution where this is just a plus 1. These two cancel out, and then we get a 1. Oh, sorry, 15. So we know that a to the 15 is 1, and when we multiply it, we get a positive power. And that's pretty much the question. Now, our next part is, we want to be able to find out the solution to this linear equation. And it might be pretty similar to what you might have done in first year math, where you essentially have to turn this into a row reduction case.
And once I can see that this is started, then we'll get into part 6 and 7. Okay, is this streaming? There we are. Okay. So that's still loading. All right, perfect. I am happy with that. Let's mute that so that I don't get annoyed. All right. So welcome everyone to the final part of part 2 of the MATH3411 revision seminar. My name is Christian. Thank you again, Ronald, for your presentation, and we'll get right into algebraic coding. So getting straight into it, we've got for a Hamming 7.4 code, so just revisit some Hamming codes. Let's consider this parity check matrix. It's arranged in the particular way that, let's change this so it's a little more contrasted. The matrix is an identity matrix followed by any sequence of vectors. So then recall the field GF of 8, which is Z2 in terms of x, modulo, or mod, quotient of x cubed plus x plus 1. And let alpha be a primitive root of that polynomial. What we'll find is that the columns of H correspond to the coordinate vectors of the powers 1, which is just alpha to the 0, then alpha, alpha squared, alpha to the 6. So we've got 1 alpha, alpha squared, alpha cubed, alpha to the 4, alpha to the 5, and alpha to the 6. So we can see that 1 is going to be the vector 1, 0, 0, because it is 1 plus 0 alpha plus 0 alpha squared. Very similar for alpha. We get 0, 1, there, there, and so on. So you can see that alpha to the 5, this column is just alpha, sorry, 1 plus alpha squared, represented by, as we can see here, column 6, because we have 0 indexed. This is 0, 1, 2, 3, 4, 5, and 6. So what we're able to do is represent the columns of H by the corresponding powers. So that is, we could just very well say it is the matrix of just 1. So that is 1 plus 0 alpha plus 0 alpha squared. Alpha, which is similar, alpha squared, so on and so forth, up to alpha to the 6, which would really be 1 plus 0 alpha plus alpha squared. Okay. So then let C be a code word. The syndrome for the code word C, given by S of C, is that parity matrix multiplied by the transpose, right, multiplied by the transpose of C, which, once expanded, becomes this, which we say is C of A, where C of X is the polynomial corresponding to that code word. This allows us to describe the code in terms of just polynomials. It's going to be very helpful to do maths with. We'll go here through a single error correcting BCH code theorem, letting f, part of z2x, be a polynomial of degree m with primitive root alpha. Let the constants n be 2 to the m minus 1 and k be n minus m. Now I'm just going to check real quick because I haven't actually checked sound. Okay, so no sound. I do just want to check. Please let me know if you can hear me. You might be able to let me know if you can't hear me. So yes, these two constants, n and k, in terms of n and m. The matrix, as we looked at earlier, is the check matrix of a binary Hamming nk code. C. So every binary Hamming nk code can be obtained in this way. For a code word, as we defined similarly earlier, we can say that, well, we can actually partition this code. So what we can say is we're dealing here with C0, C1, all the way through Cm minus 1. So those first m bits are the check bits. And then Cm onwards, Cm plus 1, all the way through to Cn minus 1 are the information bits. So it is quite nicely partitioned. So if we put some commas, partition there. It's not a part of the structure, so we'll just do it in a different color. So yes, nicely partitioned. So what we can say here, as I said earlier, the first m bits, because there are m bits in here, are check bits, and the rest are information bits, n minus m. Okay, so note that the first m bits of the code word are check bits. These first m columns are leading columns. Therefore, the information bits and check bits are neatly divided. So that's going back to the idea that I was describing as we just have an identity matrix. Earlier we had the 3x3 identity matrix. And then you can have like any kind of weird combinations going on. So let's say 1, 1, 0. I'm not actually sure whether this random matrix I'm coming up with will be proper. It could be there's like overlap that there shouldn't be. but we can see the neat partition going on here between the identity and then the weirder stuff after the identity. Okay. So then the syndrome of that code word, which we looked at earlier. Wait a minute. Okay, so that's a bit of a repeat of what we just went through, but we'll go through it again. So syndrome is the check matrix times the transpose of the code word. We get this. It's a more generalized version. So we get that is C of alpha, where C is the code word polynomial. So just formalizing what we went through earlier. Since C is the code word, its syndrome is 0. And so S of C is 0, which is C of alpha. So we can see that alpha is a root of C of x by whole ideas of year 11, I believe. Well, actually earlier than that. But since alpha is a root of C of x, the minimal polynomial m1 of x of alpha must divide C of x without a remainder. So that is to say that C of x is equal to m1 of x times some other polynomial perfectly. M1 is the primitive polynomial of f of x. Okay, so now we'll go through encoding, decoding, and error correcting for single error correcting BCH codes. Before we do that, I will just check. Nope, no one has any complaints about the sound. So from our message, Cm through Cn-1, we form the information polynomial as is below. So that is Cm x dn, Cm plus 1 x dn plus 1, all the way through Cn minus 1 x dn minus 1. Using polynomial long division, we find the check polynomial of degree at most n minus 1 as being this, and calculate the code word polynomial. The code word is, as is given here, where the first m bits are check bits and last k bits are information bits. That is, the last, we'll remember, k was n minus m. So just the remaining bits. Suppose that we receive D, which is C plus EJ, where EJ is a unit vector with 1 in the AJ position, sorry, alpha to the J position. That is not to say the jth position. We've got to be careful about that. If we were in the alpha to the 0 position, that is the 1's position, which is the first position. Alpha to the 1, which is alpha, is the second position. So first, second. So we've got to be very careful to say that it's really the J, I believe, minus 1th, no, J plus 1th position. That's what it would be, because we take 1 plus 1 to get 2. So it's much easier to think of it as the alpha to J position. And 0 entries elsewhere. So it's just as any unit vector is. 0, 1, 0, 0, for instance. That would be E sub what's in the second position. So that would be E sub 1, alpha to the 1. Let us represent C and D as their own code word polynomials, as we constructed earlier in the method of construction, as we described. Calculating the syndrome of D gives us that it is alpha to the J, namely because C to the alpha is going to be, well, we've got our code word polynomial, we can see, as being a part of it, and then we're just going to get alpha to the J as the polynomial for E sub J. We know that alpha is a root of the code word polynomial, and so we know that goes to 0. So let's actually keep this down here, equals 0. The error is therefore in the AJth position, or in the alpha to the J position, which is, as we said earlier, the J plus 1th letter of the code. If the syndrome of the code word we receive is 0, so if D of alpha equals 0, then there is no error. So if alpha is a root of the polynomial for D. To decode a code word, look at the last k bits, which are, as we've been saying on and on, the information bits. So that is the remaining n minus m bits after the first m check bits. Okay, so with now 2 error correcting BCH codes, we'll be going on to pretty soon. For the single error correcting case, we used one root of minimal polynomial, M1. We'll note a helpful theorem to expand this idea to allow for 2 error correcting. So note that if p is prime and beta is a root of some function in our field here, then so is beta to the p to the power of any I. So for any finite field with a primitive element alpha, if alpha to the s is a root of our polynomial, then so is every element of this set. So we know that in our situation, alpha to the s, that is our beta. And we are saying here, okay, if alpha to the s is root. Now, I haven't defined this properly, but here p just represents any prime. So p is any prime. So we know that beta to the, well, p to the 0, that's just going to be beta, which is going to turn into alpha to the s. And then we've got beta to the p to the 1, which is alpha to the ps. And beta to the p to the 2 is alpha to the p squared s. And so we're just forming this infinite sequence. The indices of these roots are called the cyclotomic coset containing s. And so we get the cyclotomic coset, k sub s, so containing s, is all of these powers, mod p to the m minus 1. So for the single error correcting case, the roots of m1x are alpha to the j, where j is a part of that cyclotomic coset. Specifically the cyclotomic coset pertaining to s equals 1. So I'll maybe write that over here. That is going to be the set alpha, alpha p squared, dot, 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 all of that, mod. P to the n minus 1, yeah. Right. So let's go through an example. Consider the, yes, in order to have 2 error correcting capabilities, we need a different root, not in M1x. Consider the field f defined as this finite field, quotient with x to the 4 plus x plus 1. We have p equals 2, our prime, and so we find 2 cyclotomic cosets, one of which, I'll just spell errors in my work, is not k1. So we find that k1 is this, and k3 is this. The minimal polynomial, m3 of x for alpha cubed, is, well, we get these roots. X minus alpha to the 3, x minus alpha to the 6, x minus alpha to the 12, and x minus alpha to the 9, which we can find is this polynomial, x to the 4, x to the 3, x to the 2, x to the 1, plus 1. So alpha and alpha cubed are roots of this polynomial m, defined as m1 times m3, which we can expand to get this. So the construction of a 2 error correcting BCH code is to find a primitive root of a minimal polynomial m1 of x with cyclotomic coset k1. Remembering k1, that is going to be alpha, some prime times alpha, some prime squared times alpha, all of that mod p to the m minus 1. Select an index not belonging to k1, so that is some index I in this set that is not part of k1, set minus. Find the minimal polynomial m sub I of x for alpha to the I, and define m to be that first m1, the first minimal polynomial, times our new mi. So we can see we did these exact steps. We said first, we found a primitive root of our polynomial. We then selected an index not belonging to k1, so we can see we chose 3 here, not a part of k1. We found the minimal polynomial for that root, alpha to the 3 that we chose, which ended up being this little bit. Just this bit is what we care about. And then we defined our new m as the product of our two polynomials. Then we define a check matrix. This is something we haven't done yet, but it's just 1, 1, alpha, alpha to the I, all the way through. So just alpha to the I down the bottom, alpha up the top, increasing powers. So starting at the power of 0, power of 1, power of 2, all the way through power of n minus 1. And then we define the syndrome of a code word as H, so our check matrix, multiplied by our code word transposed. And so we'll get C of alpha to the I. Okay. So far we've gone through just a lot of heavy content, so I'll just check the chats, technical difficulties. Yes, so if you would like to see some of the content that Ronald missed due to his outage, then feel free absolutely to go back and check the 3411 lecture that we gave last year. We also do have the slides on our website, and that's in the chat. Okay. So, still on 2 error codes. Encoding and decoding. Encoding a double error correcting BCH code is the same as encoding a single error correcting BCH code, with the difference being R of x, our polynomial, is I of x mod mx, where mx is used instead of m1x. So we've just got to expand on it a little bit by using our product here. So rather than m1, m1 times I, mi. For decoding, we look at the last k bits of the code word. Okay, perfect. So, error correcting and decoding, we'll go through the steps. Suppose that we receive D, which is C, our actual proper code word, plus 2 errors. We're likely going to assume here that J and L are different, but we'll have a look. So let us represent C and D as their code word polynomials. So that immediately allows us to find a connection of D in terms of C. Just using this, we will find that D of x is C of x plus, we know that EJ is going to turn into alpha to the J. We know that EL is going to turn into alpha to the L, or we'll say x in this situation since we're dealing with x to the power of L. Calculate the syndrome. So we can see the syndrome of D as we saw a little earlier, just back here. We know that the syndrome of a code word, or the syndrome of anything, is going to be its polynomial evaluated at alpha, and then its polynomial evaluated at alpha to the power of I. So we get exactly that. Subbing in this little relation we found, we're going to find this is C of alpha, alpha to the J, alpha to the L. And the same with powers of I. We know that this will go to 0, and this will also go to 0. And so we get this is going to be S1 and Si. Syndrome allows us to determine when there is 0, 1, or 2 errors. If there's 0 errors, well, that's going to be the case when d of alpha equals d of alpha to the 3 equals 0. I feel it was a mistake to pick 3 here. I think that's more harkening back to the previous example. 1 error when d of alpha is non-zero, and yes, so when you can take out or put in the power of 3, and 2 errors when d of alpha is non-zero, and you cannot take in the power of 3 or take out the power of 3. So really here it should be power of I. So let's just modify that. That should be an I. 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 And that should be an I. Okay. So we'll go through an example question. Let M1 be this polynomial, x to the 4 plus x plus 1, in Z to x. And F be the field of Z to x, quotient with our polynomial x to the 4 plus x plus 1. Let alpha be a root of M1 of x, and we may assume that F is a field with the following description of its non-zero elements. So we are going to get that alpha to the 0 is 1, alpha to the 1 is alpha, alpha to the 2 is alpha squared, alpha to the 3 is alpha cubed. So all very standard. We're going to get that that corresponds to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So we know that those first 4 bits are going to be just the identity matrix. And then we'll get alpha to the 4 is 1, 0, sorry, 1, 1, 0, 0. I'll maybe do a few more just to show the construction of this matrix. Alpha cubed is 0, 0, 1, 1, and we'll do one more. So we get 1, 1, 0, 1. So that is 1 alpha, no alpha squared, alpha cubed, so on and so forth. I'm not going to write the rest because we're only halfway through all of that. We are to figure out what alpha to the 10 and alpha to the 11 are. So the trick here is to express alpha to the 10 as a linear combination of some powers that we already know. So we want to do it as 1 plus alpha squared plus alpha cubed because, well, you should be able to reduce everything past this point, past the identity matrix point, into powers of alpha contained in that identity matrix. So that is these 4. Let's emphasize that. So what we do is we take advantage of the fact that, oh, we know the one immediately preceding it. That is alpha to the 9. So we express alpha to the 10 as alpha to the 9. Alpha outside of, well, we already know alpha to the 9 is alpha cubed plus alpha, which is alpha to the 4 plus alpha squared. But again, we know alpha to the 4 is alpha plus 1. Subbing that in, we get alpha squared plus alpha plus 1. And now that we have this answer, we can use a very similar technique on alpha to the 11. We can say it's alpha times alpha to the 10, which is alpha outside of what we just found, which is alpha cubed plus alpha squared plus alpha. And that's it. So rewriting them all, which you likely wouldn't do, but doing so anyway, we get these 2 answers, exactly what we wanted. Now, let's have a look at solving a set of linear equations in our field. So what we're able to do now, okay, so we'll have to go through this because this is a same problem. Okay, so we'll treat this like row reduction. We know that this is going to be alpha squared, alpha to the 4, alpha cubed, alpha to the 4, alpha to the 8, which goes to, now let me just check, did I include the solution properly? BCH code is obtained from message. Polynomial of alpha cubed using its message. Yeah, no, so I didn't include it. So using our techniques of row reduction, we'll multiply all of this row by alpha. We'll get alpha cubed, alpha to 4, alpha to 5, alpha to 5, alpha to 3, alpha to 3, alpha to the 8. I am hesitant to substitute in what we already know these alphas to be, just because I think it's going to become quite a large problem. We'll do that in a moment when we have to combine things. So I'm going to take this second row and subtract from it the first row. So we get alpha cubed, alpha to the 5, alpha to the 5, nothing changes there. We then get here, well, that's going to be just 0, which I don't worry about right now. And then we'll get here negative alpha to the 2. So what I'm in fact going to do is I'm going to make this second row the first row minus the second row. So this is going to be alpha to the 5 minus alpha cubed. And this is then going to be alpha to the 5 minus alpha to the 8. So we can simplify those. Let's add a page. We know alpha to the 5 is equal to, going back here, alpha squared plus alpha. We know alpha to the 8 is equal to, going back here, alpha squared plus 1. And so when we do alpha to the 5 minus alpha to the 3, we're going to get that that is alpha cubed, alpha to the 5, 0, alpha to the 5 minus alpha to the 3 minus alpha to the 3 plus alpha squared plus alpha. Leave alpha to the 5, and we will do this as alpha to the 5 minus alpha to the 8, which is going to be alpha minus 1. And then we can continue with this, alpha cubed, 0, alpha to the 5, which will turn into alpha squared plus alpha. This can be alpha squared plus alpha, alpha minus 1, and negative alpha cubed plus alpha squared plus alpha. Now, this is just going to take a very long time to do, but if we continue row reduction, we should get to our answers. We do also have access to solutions for these problems if you want to check the rest of that working. So then, I didn't make a solution for this problem either, so we'll have to just have a quick read over it. BCH code is obtained from F by replacing a message C8 through C14 by the coefficients of a polynomial Cx in Z2 of x, where C of x is Ci plus Cr of x, Ci is this polynomial, Cr of x equals Ci of x mod mx, and mx is this polynomial that we actually got quite a bit earlier. M3 of x is x to the 4 plus x cubed plus x squared plus 1, which is the minimal polynomial of alpha cubed. Using this code, encode the message m equals 1110001. So we'll go back here to the steps of encoding a message such as this one. So let's have a look. Where are we? Correcting and decoding, encoding and decoding. Okay, so encoding a double error correcting BCH code is the same as encoding a single error BCH code, with the difference being R of x is that. So exactly what we have down in our question. So we'll go to encoding a single, and where are we? Here we are, BCH encoding. So from our message, we form the information polynomial. So we go down to our question. Let's insert a page. So first step, we construct our information polynomial, which was defined as, where are we? So that's 2, and we are going to 1. Cm x to the m, cm plus 1, x to the m plus 1, all the way through. So we'll figure out what m is in this case. So where are we? There we are. Okay. So we say here, our code word polynomial is cm x to the m, cm plus 1, x to the m plus 1, all the way through to cn x to the n. Okay. We go back to here. Maybe I'll add a bookmark so it's easier to get to. Don't know where bookmarks are. There we go. All right. So we form the information polynomial. Then using polynomial long division, we find the check polynomial of degree at most m minus 1. Okay. So we want to find the check polynomial here. So we know that m was, where was it? I haven't done this question in a while, so I do regret not having written down the solution. Okay. I may need to update the slides before we upload them, just because I want to be timely about this, and we still have a section to get through. So yeah, my apologies for that, everyone. I'll go about correcting the slides before we upload them, but it will be following those same steps. So apologies for that. But we'll get on to cryptography of ciphers. So we'll remind ourselves, a message M is plain text and is encrypted using an encryption function E sub k into an encrypted message or the ciphertext C, which is a part of our word dictionary. The encryption and decryption function depends on a key K. So there should be a capital K down here because it is dependent on our key. The decryption function is the inverse of the encryption function. So we say that the decryption function, d sub k, if you put that on top of the encryption function, you just get the original message. We can assume that cryptanalyst knows about the design E sub k and the set of all possible messages M, but they don't know the key, and ideally should be able to decrypt the message without it. So we've got first simple monoalphabetic substitution ciphers. So that is where they replace each letter with another symbol, A being exclamation mark, B being question mark, so on and so forth, or we apply a permutation pi to the letters A, B, all the way through Z. If we apply permutation, there are 26 factorial total keys. So that's 26 ways to pick A. So we could assign A to, well, A. We could change it to B. We could change it to C. Maybe I'll say we'll do here 1, 2, 3, 4, all the way through 36 different options. Sorry, 26 different options. If we choose some substitution alphabet of length 26. Then once one of those letters has been picked, there are only 25 ways to pick for B, and so on and so forth until there is one remaining way. So that's 26 ways for A, 25 for B, 24 for C, all the way through till 1 for Z. So that's 26 factorial. For encryption, we just say that the encryption sub pi is pi of I, and decryption is pi inverse. A transposition cipher means for us to divide the letters into blocks of length r. So say if we had the words, what, good word. And we picked an R length of 4. So we'd say that's a length of 4. That is a length of 4. What we do is we apply a fixed permutation to the letters on every single block. So for R equals 4, we can have this permutation. What it means is that the first letter goes to the second position. So let's highlight this in red. The first letter goes to the second position. So that is what this column represents. 1 goes to 2. And you'd find also then that 2 goes to 4, 4 goes to 3, 3 goes to 1. And so we have this sort of 1 to 2 to 3 to 4, back to 1 rotation. What that means for us is that a message like math, well, the first position would go to the second position. M in the first goes to M in the second. What was originally in the second position, let's have a look here. So let me check if I've done this right. A goes to, okay. I think I've done this wrong. Good. All right, so A should go to the third position. So M goes to second, and then, well, we can actually simply write, no, that should be right. So we know that 1 should go to the second position, 2 should go to the fourth position. Oh, I see what I've done. I've just written this out wrong. No, this is correct. 2 goes to the fourth position. I just misread that. Then 4 goes to the third position, and 3 goes to the first position. My apologies for that, everyone. So this is, in fact, correct. M in the first position goes to M in the second position. A in the second position goes to A in the fourth position. T in the third, T in the first, and H in the fourth goes to H in the third. We can use a substitution and then a transposition to make codes harder to break, both of which are easy enough to decrypt just by applying their inverses in correct succession. Then we have polyalphabetic substitution ciphers. So let's have a look at the Virginia cipher. There are different Caesar ciphers applied periodically according to a key. Caesar ciphers shift each letter k places forward. So those are just our examples of polyalphabetic substitution ciphers. And then there's Kasiski's method. This method is used against the Virginia cipher, and it estimates the length of a key. The index of coincidence, I sub c, is an estimate of the probability of coincidence, PCM. The probability that 2 randomly chosen letters from a message M are in fact identical. So a formula given for Kasiski's method is for a message M of length n, the index of coincidence, so index of coincidence, an estimate of the probability of coincidence, the probability that 2 random chosen letters are identical, is given by the sum of fi squared minus n over n squared minus n, where fi is the frequency of each letter in the message. Now, an estimate, which has gone slightly off the page, is for the key length of a periodic substitution cipher, is around about this. So just some constants that we won't particularly get into where they come from, namely because I don't know where they come from. Also because we can just use the formula. We don't particularly need to know the roots of the constants. Now this down here should say an I sub c. So I'm just going to write this on the next page. Clearly. Oh, no. There we are. Okay, no, so we're all good. I did end up fixing that. So let's have a look at a question. Kasiski's method. This is from, I believe it was actually 2019. Question 3i, so 2019 paper. We have an English language message has been enciphered using a Virginia cipher. So this is the message encoded. Spaces and punctuations appear in the text as they do in plain text, so we don't have to worry about commas or spaces representing letters. We can be confident that the contents of the message are strictly held in these little islands of letters. So the letter frequencies of the ciphertext are as follows, given by odd and even letter positions. Calculate the index of coincidence, IC, of the message. So if we have a look here, just for instance, A shows up in the even number positions. We have even number positions being in blue here. There, 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 there. Just continuing to show this in. Let's give this just a moment, so everyone. And there we go. So we can see that A shows up colored in blue here, here, and one more time over here. So we can see that that shows up 3 times. So odd is going to be red, which is here, and even is going to be blue, which is going to be here. Calculate the index of coincidence will be our first question. So what we'll do is use the formula we just looked at, I sub c. So we know that n is 51, that is the length of the entire message. Each value f sub I can be found in the table with letter frequencies. For example, the frequency of the letter capital A is 2 plus 3, which is 5. So the index of coincidence is calculated to be this figure. So we've got 5 for A, we've got 2 for B, and we'll have 2 here for Z. Yep. Subtract 51 over 51 squared minus 51. So we end up with that simplifying to 61 over 1275, which is around about that. So that is the index of coincidence. The probability will remind ourselves that 2 randomly chosen letters from a message n are identical. Okay, so let's delete that extra page. I had thought originally, when this was clipping off the page, honestly looking back, it was a bit stupid that I didn't just scroll. But no, there was an issue I had earlier that I didn't realize I'd fixed. Okay. So now we'll go through question B. Question B is estimate the keyword length using the estimate we were given prior, where n equals 51 is the total number of letters. So we can simply just substitute in the approximate index of coincidence and estimate the length of the key by also subbing in n, n minus 1 and n over here, interspersed by constants. So let's just highlight what each individual thing is. So we've got a weird constant, weird constant, weird constant. Shows up here, here, and here. We've got n showing up there, there, and something to do with n there. And then we've got I sub c showing up here. And honestly, I'd actually suggest using just the exact value. We should have used here 61 over 1275. So use 61 over 1275. It can't hurt to be slightly more accurate, especially since we're already approximating. But we get about 2.87, 2.82, yeah. And so that's the estimate length for the key. Then for questions C and D, so question C is, for such a short ciphertext, this particular estimate is not accurate. Luckily, we can decipher such a short ciphertext by trial and error, and it turns out that a keyword of length r equals 2 was used. Find this keyword. So just through trial and error, we can find the key and decipher the message as a wonderful message from Brett himself. Dear all, I hope you crush the exam and enjoy the course. I always love these messages when I do the course. And then public key cryptography. In a new form of cryptography known as asymmetric cryptography, there is no longer a common key. So the sender and the receiver do not have to exchange keys. The public key k corresponds to a set of encryption functions, e sub k, and the private key, k bar, corresponds to a set of decryption functions, d sub k bar. For all k, there exists a k bar such that there's a decryption function to decrypt an encryption function. So there is an inverse to each encryption function. E sub k of m is c, and d sub k of c equals m are easy to calculate, so you don't need any sort of a supercomputer to do so. Without knowing k bar, E sub k of m equals c is hard to invert. Now that should be E sub k bar. So the entire idea of it is easy to calculate, hard to invert, as is all decryption and encryption. In the RSA scheme, each user does the following. Choose two large prime numbers, p, q, and n, which is the product of those two, and then take phi of n to be p minus 1, q minus 1. Choose a random e, not our regular e, just some polynomial, between 1 and phi of n, for which these two numbers, e and phi of n, are coprime. Their greatest common divisor is 1. And find d, which is the inverse of e mod phi of n. So we know from what Ronald said earlier that if the GCD is 1, then there is some unique inverse, d, modulo phi n. So k is the pair n and e, and k bar is the pair n and d, where the encryption is e sub k is m to the e mod n, and the decryption is very much the opposite. That is c to the d mod n. So m is our original message, c is the encoded code word message. So we get that d sub k bar of e sub k of m is m to the e to the d, which is m to the ed, which is m, because we know e and d are coprime, and not coprime, they're inverses, mod n. So these are all equivalences. So yes, as I said. Okay. So an example RSA question, consider the following encryption scheme. Ignoring the rare letters J, Q, X, and Z. We can see J, where are you? Nope, just got numbers. We just know that they're rare to show up in messages. Triples of letters S1, S2, and S3 are encoded as numbers by mapping the letters A1, A2, and A3, respectively, using this encoding. So A is 1, B is 2, C is 3, so on and so forth. Again, we ignore J, Q, X, and Z. So A, B, C, D, F, G, H, I. We've ignored J. We've just skipped it. Then replace A1, A2, and A3, the triple, by 23 to the 3, A1, plus 23, A2, plus A sub 3. So for example, day, which is, we can see here, D, A, Y. That is going to be 4, 1, and 22 is 4 by 23 squared, plus 1 by 23 plus 22, which is 2161. This number is then encrypted using RSA encryption with a very large n. And encryption exponent, that. Using Fermat's factorization or otherwise, factorize n. This is our first question. So just using the factorization theorem, we can, we can factorize 14646 into 2 primes, 97 and 51. Then show that phi of n is 14400. So we calculate phi of n, we remember it's our first prime minus 1 times our second prime minus 1. 14400. Calculate the decryption exponent, showing working. So we know the decryption exponent is going to be, well, we want E inverse. So we calculate the inverse of 12343 mod 14400, which we get to be 7. You can do that through a few different methods, such as the extended Euclidean algorithm, if you want to have a look at that. And then we will decipher the received ciphertext, C equals 4729, giving the answer as a 3-letter word. So deciphering the code through the method we know, we end up with that being 11683 mod 14647, which we can uniquely decompose into this polynomial of 23s, because we can see this is essentially an x squared, and this is an x, and this is a constant. It's very important that these powers, these x's, were chosen to be greater than any coefficient, so that they can be uniquely captured as this polynomial method. And so we can decompose it like this by first taking 11683 mod, well, 23, and that will eliminate these two, and we'd get that that is going to be equal to 22. And then once you take away 22 from this, you get 11661 mod 23. Well, we'd actually divide by 23, so that then we'd technically just be dealing with 23 by 22 plus 1. And so mod 23, we're going to get 1, and we do very similar to get the 22. So this corresponds to 2212, which is yay. So that was just a nice little example, RSA, of public encryption-decryption. Unicity distance is a concept that represents the minimum amount of ciphertext required for a unique and meaningful decipherment when trying all possible keys. So unicity distance as a formula is defined to be the ceiling of h2k over log 2q minus r, where k is the total number of keys, q is the number of letters in the source alphabet, and r is the rate of language in bits per character. So for an English text, such as an alphabet including 26 letters, our standard alphabet, and r is around 1.5, r is the rate of language in bits per character, we get n naught, which is our unicity, being this, being this, being this. If the keys are equally likely, then we can say that h2k is approximately, or actually exactly, h2k would be, but unicity would be approximate, log 2 of absolute k, so log 2 of the size of k. So an example, 2018, question 3, triple I. A product cipher on English text, 26 letters, is formed by applying a simple substitution cipher and then a transposition of length 9. We'll remind ourselves transposition a little bit ago. That was just one of these matrices that sent 1 to 2, 2 to 4. I believe we did 3 to 1 and 4 to 3. Yep, that's about right. That's not what it would be in this case. We'd actually, this is a length 4, applying 2 blocks of 4 length. we would actually have this be length greater, it would be length 9. So find the number of possible keys, find the unicity distance for the cipher. There are 26 factorial. Did I get transposition mixed up? I got transposition mixed up with, let's go back to the beginning. Transposition was mixed up with permutation. So there was transposition. That's okay. We'll follow the solution. So there are 26 factorial ways to apply a substitution cipher. There are 9 factorial. No, I got transposition right. Okay, cool. So apply transposition of length 9. Therefore, total number of keys is absolute k, which is 26 factorial times 9 factorial. And then the unicity distance, well, we'll use our approximation. Remember, approximation. Log base 2 of k over 3.2, which is around about 33.4. And then part C of that same question was a message of length 50 is enciphered using this product cipher, and the resulting ciphertext is intercepted by Eve. Imagine that Eve could try all possible keys of the product cipher in order to try to decipher the ciphertext. Would Eve expect to decipher the text in a unique and meaningful way? Well, we know the unicity distance, 33.4 approximately. Since the message of length 50 is larger than 33.4, so we know the length is greater than n naught. Even though this was an approximation, we can be confident that the approximation is at least within the bounds of something to the order of 20 of a difference. Eve, my mistake, should be able to decipher her text in a unique and meaningful way. And that's it. Okay. So, yes, as I said, I'll have a go through the slides and write solutions for those 2 questions that I didn't have solutions for. But other than that, that'll be about it for today. So thank you everyone for attending these 3411 revision seminars. I wish you all the best of luck, and today is a special day just because for quite a few of you, for me at least, we have enrollments for classes next year starting today. So make sure at 2, if you do have